And after that, again, uh, from pi minus theta to 2 pi, it will be e into d omega t. And we just need to solve this expression. So let me solve it for you. In last session also, I left one problem just to calculate those values. Did you get the answer correctly? So E is here 200 into theta minus 0. Theta is 38 minus 0. You have to convert it into radian first. Okay. Plus Vm sin omega t d omega t. It will be minus Vm cos omega t. So you will get 2 Vm cos theta for this integration only, right? Sin omega t minus cos omega t, and cos theta minus cos pi minus theta would be again minus cos theta, and you will get 2 Vm cos theta plus again E, which is 200 into 360, 2 pi 360 minus pi minus theta, which would be pi plus theta. So that is 180 plus 38 into, which is converted again into radian. So now you have to solve this expression, and that will come out to be, mm, let me calculate it. So 200, 180 plus 8. So this E term has the component of 893 by 6, sorry, 0.6 by 2 pi plus this 2 Vm cos theta, that is cos 38 into 2 into 230 into 2, that is 512.63 by 2 pi, 893 by 6 divided by, it is 223.8 volt. So you got output voltage just after drawing the waveform. So first you need to identify the nature of output voltage waveform, which is very easy to identify just after analyzing which switch is conducting at what instant, and then you will get clear idea. And if once you get the output voltage waveform, then it would not be a big task to calculate the integration of that. And if that is done, now if V naught is done, we need average charging current. So here V naught we calculated, and if we apply the KVL in this loop, if you apply KVL in this loop, so V naught will be I naught R plus E. We calculated V naught. E was given in the problem. R is also given in the problem. So we are just left with I naught. So that I will calculate. I naught will be E naught 223.8 minus 200 by 2, and that will be 11.9 amperes. So it was the answer for this problem. And if you would have been asked like which type of current waveform it looks like, so you could also draw that. It will conduct, means current waveform will be visible after the point when current is getting supplied from your source side, right? So it will be like this, and it will be zero because after this period no other switches are getting conducted. So it will conduct for only from pi minus theta, sorry, from theta to pi minus theta. So conduction period of your this circuit for the time it will conduct. So circuit conducting time that will be pi minus theta divided by 2 pi, right? So you will get the value whatever, or maybe you can divide it by omega, so you will get in terms of seconds. Otherwise, you will get in terms of angles. If you divide it by omega, then you will get in terms of second. Omega is nothing but 2 pi into f. F is 50 hertz. So that you can do. Okay, 180 minus 38 minus 38 by 2 pi into 50. Right. So any doubt in this problem?
No, sir.
Okay, then we will go ahead. So this is another problem which was asked, and we just need to judge the answer of this problem just by looking at the circuit. Okay, so it has been asked. Let me zoom it out. So it was said that a single phase half wave uncontrolled converter circuit is shown in the figure. Uh, and this converter circuit, this entire rectifier circuit, is connected by a two winding transformer. And here the supply, which is V, is Vm sin omega t was provided. We just need to identify the current waveform to diode D2, this D2. Though I haven't discussed any freewheeling diode operation or any kind of waveform, uh, the next topic which I am going to discuss is like semiconverter. So there you will get proper idea of how freewheeling diodes will work. So, but it is very intuitive, right? We can judge from this problem because during preparation we should or we get to learn many concepts through problems only, right? That's why we generally solve so much problems so that we grasp all the concepts and most importantly, how to apply those concepts in problems. So those things are most important. So that's what we are doing right here. So we need to identify the current waveform of D2. However, we haven't discussed any characteristics of D2, but we will see what will happen. So see, uh, when supply was positive, when Vm sin omega t, let's see, this Vm sin omega t is positive. Okay, this is Vs. It means this diode will be forward biased. Okay, which means this diode will be reverse biased. How come? Because you see the polarity here, and this polarity is not appropriate for this diode to get turned on, right? So this diode will be turned off and this diode will be turned on because it is connected to positive terminal. And this load, whatever the load is, since inductor is the indicator to understand that the load is drawing constant current, right? That's why this statement is also mentioned. Even it was not mentioned, we would have assumed that, yeah, if inductor is present there, it means it is indicating that our load current meant to be constant, and it means is we need to identify the current waveform through D2. So D2 will definitely not conduct for first half cycle, right? When supply is positive, when Vm sin omega t is positive, which is L di by dt, it means di by dt is greater than zero, right? Since this Vm sin omega t is positive, inductance value will be positive since it is a passive device. It means it will be greater than zero, right? So it will charge since di by dt is getting increased. It means it will charge for first half cycle. Now, if voltage is becoming negative, that definitely will become because sinusoidal nature is such that it will be positive for half cycle and negative for half cycle. So when this polarity is getting negative, it means now this diode will be turned off and it will be turned on. So whatever energy was stored in inductor during positive cycle, now it will become an active source and it will supply its energy, or it will free will its energy through diode D2. Okay. And whatever the time constant of this circuit will be, at that rate it will discharge its energy, and hence the D2 will definitely conduct at least for pi period, another pi period, and that is the next from pi to 2 pi. So this was the reason to frame this kind of problem. So the concept behind that. If this diode is there, it will freewheel its current through diode D2, whatever the load has consumed or inductor has stored energy during initial pi period, right? So it was bit intuitive, and the role of diode, freewheeling diode, would have become a bit clearer, I guess, or bit understandable. So more about freewheeling diode we will see in next topic, I guess. Yeah, any doubt there? Please go ahead.
No, sir, clear.
Okay, thanks. So this was second problem. Third problem we will see. Yeah, again, this topic was not discussed during the full bridge rectifier of single phase. Uh, can you tell me which topic is this, which is not covered? By just observing the circuit here, which kind of circuit you might have gone through some concepts of this kind of circuits.
Center tap or rectifier.
Yeah, perfect. That's great. So it is nothing but the center tap rectifier, and only one kind of problem has been framed based on this circuit, that is just to calculate the peak inverse voltage across the diodes. And its operation is not much different. If you know when which switch is getting turned on and when which switch is getting turned off, then you can easily know that the what will be the characteristics of your output voltage waveform. So here also in this problem, as usual, they have asked to compute peak reverse voltage, which is nothing but the peak inverse voltage. Okay, so it is uh, not some serious thing, but we will see this problem how to approach any problem for computing peak inverse voltage. So it was supplied with 230 volt 50 hertz AC, and it is getting transformed to like in a step down manner. So it will be 50, okay, 0 and 50. So it does mean by this kind of notations that this type of polarity will be here, which is quite obvious. Okay, when this terminal is positive, right? And since it is AC and sinusoidal, so this kind of polarity will be for only first half cycle. Okay, first half period. Again, it will change, but it will not affect the peak inverse voltage. Why? Because whatever change will occur in the polarity on primary side, the same will reflect on the secondary side. Okay, so we do not need to bother about it. And at any time, you can see by this diode, at any time for continuous operation. For what I mean by continuous operation, for one half cycle, this diode should conduct, D1 should conduct, and for another half cycle, D2 should conduct. As usual, as it was happening in full bridge rectifier, where T1, T2 was conducting for positive cycle and T3, T4 was conducting for negative cycle. Right. Right. So, and you can also see from the notation, if this notation is proper or not, you can verify it, right? If this terminal is positive, it means this diode is gonna turn on, right? And this diode is connected to negative terminal, so this is definitely gonna turn off. So you can see that at any instant, this only one out of two diodes will conduct. Right? So that's my point, and that's the entire philosophy behind center tap rectifier. But here, the question is a bit different. They have asked peak reverse voltage. So we can draw this kind of polarity, and if we can draw this kind of polarity, then nothing else left. Let us assume this D2 is turned off, right? So if D2 is turned off, it means it will have some voltage of VD, right? And its polarity will be in the manner what I have represented here. Why so? If I write like this, it means it has positive voltage, and for ideal diode, if it will conduct, it means voltage across the diode will be zero for ideal diode, right? And generally, for theory purpose, we assume everything ideal, and hence I denoted it as minus VD. So now we just need to apply KVL, right? So I can write it, I can go in this manner, and I can apply the KVL, and I can write minus VD, right? Plus 50 volt, and again plus 50 volt is equal to 0. So we will get VD is equal to 100 volt. Okay. Uh, is it correct? VD 100 volt.
Yes, sir.
Yes, sir.
Yeah, it is correct, and it was in the option. But one silly mistake we did not multiply it with root 2. Right? So the peak voltage, whatever, that will be for any particular instant, and here also it would have been 230 into root 2, and if it is getting transformed, it is becoming 50 into root 2. So we need to multiply it with root 2. So answer was 100 root 2 volt. So that's why every time when people mention peak inverse voltage across peak inverse voltage across these diodes in center tap rectifier, that will be 2 Vm, and Vm means the peak value, okay, not RMS value. Okay, I hope this is clear, right?
Yes, sir.
Okay, perfect. One last problem we will see, and after then we will move to a bit theory part. So again, I did not discuss any inductive load, and I wanted to discuss it with a problem again. So in the problem, it is asked that a half-wave thyristor converter supplies a purely inductive load. It means there are no other resistances, so whatever it will store the energy, it will have to dissipate along the source only or devices. Nothing else are there. And they have made it a bit complicated, and triggering angle they have made is 120 degree. Okay, so alpha is 120 degree. So they are asking for extinction angle, means beta, or whatever you can call it, extinction angle. That is, the definition of extinction angle is the point in the same time period when the switch has started conducting, two, not two, uh, in that same period when it will stop conducting, again in the same period. Okay, let's assume any particular period of time for mm 2 pi. So this is one time period, right? So uh, that triggering angle or firing angle is such that when it started conducting in this time period to the time period when it stops conducting in the same time period. So let's assume it can stop conducting here, beta 1, or here, beta 2, anywhere. So that is known as an extinction angle. So we need to find out the value of that extinction angle. Okay, so we will see that what will be the angle. But just in layman term, I will tell first that it will charge for whatever duration of time. It should get discharged in that much duration of time, right? So since it is an ideal inductor, so voltage across an ideal inductor will be zero in one time period. It means the rate of charging should be equal to the rate of discharging. That we will verify with uh, expressions, some expressions. So that is VL is equal to when this thyristor is fired. So Vm sine omega t is equal to L di by dt, and this di by dt is nothing but Vm sine omega t by L. And if I integrate on both the sides 0 to IL and dt from 0 to t. Okay. And if I would make it a more detailed, so it will conduct from alpha, right? So uh, we can write it more appropriately in terms of alpha, since it is getting uh, it is starting its conduction from point alpha and it will stop at beta. Okay, so it will be like that. And sine omega t also has a variable in terms of t, so it should be inside integral. So let me just modify it. So from alpha to beta. Is it fine till now? Now,
Yes, sir.
okay. So we can again we integrate Vm sine omega t is minus Vm cos omega t, right? By omega L. Since it is in dt, so omega would come on the denominator side, and since it will be from alpha to beta. Just a second, please hold. हेलो. हाँ. हाँ बोलिए, जल्दी बोलिए, क्या कुछ काम. हाँ ठीक है, बाद में करते हैं. हाँ, so it will vary from alpha to beta, and if I put those values, so it will be Vm by omega L cos alpha minus cos beta. Okay, this is the value of IL. Now we want to compute the point of extinction angle. So at that point, IL should be equal to 0. And if I am equating IL is equal to 0, what I mean indirectly is cos alpha is getting to be equal of cos beta. So when this condition satisfy, cos alpha is equal to cos beta, it means there will be one relation in terms of alpha. So beta is 2n plus minus 1 alpha, right? No, sorry, 2n plus 1. See, when alpha was 120 degree, so cos beta should have some value which should be equal to cos alpha. So that means 2n pi 2n minus plus, I guess, 2n plus minus 1 pi into alpha, I guess, mm, into hmm, 2n pi minus alpha, right? Sorry, these are some trigonometric identity. 2n pi plus minus alpha. Yeah, now it makes sense. Yeah. If you put beta is equal to 2n pi plus alpha or minus alpha, let's assume n is equal to 1 and assume this minus alpha. So after putting n is equal to 1, beta is 2 pi minus alpha. So if you put cos 2 pi minus alpha and alpha was 120 degree, it means cos 240 degree is equal to whatever this cos 120 degree, right? So since cos 240 is also positive in third quadrant, cos is positive. Sorry, this is third. Sorry, fourth quadrant, cos is positive, and 240 sine tan cos whatever. So basically, what I mean to explain here is if you put beta is equal to 2n pi plus minus alpha of any value of n, you will get the same value of extinction. So beta was extinction angle. So in for this problem, for this particular problem, it will be 240 degrees. So and what I explained in layman terms that since it was getting triggered at 120 degree, uh, so for whatever period it is getting charged, let's assume this is middle point 180 degrees. So it was getting charged for 60 degree. If it would have conducted for entire 180 degree, it would have been discharged for another 180 degree. Since here it is getting charged for this 60 degree, it will be discharged for next 60 degree and 180 plus 60 is 240, and that you can verify it from the expression as well, which is 2n pi plus minus alpha. I hope this would have been fine.
Yes, sir.
Okay then. So these was all four problems, right? So I hope these problems would have given some insight which type of problems has been framed in GATE exams. Let us move ahead with our discussion on semiconverters. So what are semiconverters and why do we even use semiconverters? Yeah, so basically it looks like it is a full bridge rectifier. If I draw it, it will look like it is a full bridge rectifier, but with slight changes. What are those changes? Can you guess or do you have any initial idea?
Diodes will be used as
Uh,
well as thyristors.
yeah, correct. That is correct. So how many diodes will be replaced?
Two.
Two. Perfect. Two diodes will be replaced with, sorry, two thyristors will be replaced with two diodes when we are talking in terms of full bridge controlled rectifier. Or if you talk in terms of uncontrolled rectifier, two diodes will be replaced with two thyristors. So of course, uh, there are redundancy of two switches. So if you compare it with full bridge controlled rectifier, first advantage you will get in cost reduction. Okay, cost reduction. Second, control. Control is so you have better here. Okay, control is easier. Okay, fine. So how does it operate? That what we will see. Let us assume again a standard T1, T2, or D2, T3, D4. This particular configuration is known as symmetric. Why this is symmetric? First of all, both are like symmetric. If you draw any axis like that, it will look symmetric. Second reason is more technical that we will derive. Again, the supply is Vm sine omega t. Okay, so when Vm sine omega t is positive for positive supply, okay, we will talk from instant alpha, okay, from alpha to pi. We could discuss from 0 to alpha also, but that I will keep it for last. So from alpha to pi, since both switches will be in sync T1 and D2, and at alpha this T1 will be on, so T1 and D2 will be on. It will operate as a normal rectifier. Fine. From pi to pi plus alpha, which two switches will conduct? Any guess? Since for sorry, till the point of pi plus alpha, this T3 is not gonna turn on. Okay? Our D2 is going to turn off. Okay, D2 should not conduct after pi. D2, a scope of D2 is cancelled. Okay, T3 is also not going to turn on. So we are left with T1 and D4, right? So of course, two switches will turn on. But what will happen when T1 and D4 will conduct? It will create some freewheeling action as if they have a diode connected, freewheeling diode. If freewheeling diode would have been present here, that diode would have conducted, right? But those diodes are not present for now, so they will freewheel across T1 and D4. Since T1 is not going to turn off until T3 is going to turn on, right? And this D4 is immediately turned on as we crossed the instant pi. So T1 and D4, but they are doing freewheeling action. Okay. So for clarity, we will remove this. Now, after pi plus alpha to 2 pi, which switches will conduct? We can guess after pi plus alpha, this T3 will be triggered at pi plus alpha, right? And the other switch D4 was already turned on at pi, so it will definitely conduct. So D4 will conduct. Any confusion till this point? Or am I going fast? Should I repeat these points?
No, sir, got it.
Okay. Last is 2 pi to 2 pi plus alpha. And whatever device will conduct for this period, those devices will be same for 0 to alpha. And that's why I did not discussed 0 to alpha initially. Now you would judge better which devices would conduct for this period. Make any guesses?
D2, T3.
D2, T3. D2, T3. Perfect. Yeah. They will free will, right? So D2, T3. Yeah. So D2, T3 will free will for the instant 2 pi to 2 pi plus alpha, which is same as 0 to alpha. Now we know the switches, which switches will conduct when. We can easily draw the waveforms, right? This is alpha, this is pi plus alpha, this is 2 pi. This is the waveform of PS. Now, yeah. So for 0 to alpha, we are now drawing the waveform of V naught. So for 0 to alpha, D2 T3 was freewheeling, right? D2 T3 was freewheeling, and when they freewheels, it means V naught is equal to 0, right? They are making a short circuit path, so V naught will be 0 till alpha. And after alpha 2 pi, the switches were T1 and D2, and this T1 and D2 is conducting, and they will follow the supply voltage waveform. It will immediately start following the supply waveform till pi. Right? Again, pi to pi plus alpha, two switches were freewheeling, and those switches are T1 and D4. So let me also write it by D2, T3. Here T1, D2. Now from pi to pi plus alpha, it is T1, D4. Again, it will not conduct for duration pi to pi plus alpha. And then from pi plus alpha to 2 pi, it is T3 and D4, and T3, D4 is connected to the reverse of supply, so it will again follow minus Dm sine omega. So this is again periodic with half of the time period, right? Uh, it is your waveform. Now we have the waveform, we can easily compute the average value of this circuit. So we will take only pi period from alpha to pi, which is Vm sine omega t d omega t, which will come Vm by pi 1 plus cos alpha. If you integrate this, you will get this output voltage waveform. Okay, so that was all about output voltage waveform. Now we need to find some more things which are known as source current, THD, and all. So, okay, first we will compute the source current waveform or RMS value of source current or whatever. So source current would look like similar to our load current, and we will again assume that our load current is continuous. So mm, when these freewheeling diodes were conducting, let's suppose T3 and D2 and D4 and T1, not it is not right to call it freewheeling diodes. When freewheeling operation was happening in this circuit, then source current is zero, right? Source current is zero because freewheeling action only relates output side. It is only relevant to load side and only it will be limited from load to the devices. It is not going to reflect in source side. So definitely because of that, no any supply current is being withdrawn. So that means that source current would be zero for that freewheeling operation period. It means we can draw IS as zero for those period if I want to draw it. So this is the waveform of IS. It will be zero. But whenever the switches are conducting, which is connecting source to load for those period, like from alpha to pi, and since T1 and D2 is conducting, it means IS is flowing in that manner, right? T1 and D2. T1 and D2. So it will go enter T1 and it will return from D2. And IS we will consider positive here. So it will be positive till pi. Again, from pi to pi plus alpha, it will be zero due to freewheeling operation. And from pi plus alpha to 2 pi, IS will be equal to minus I naught because T3 and D4 is conducting. So it will go through T3 and D4. So if you see D4 is connected to this side and this current will come from this positive circuit. So IS sign is getting reversed or direction of current is getting reversed. So I am inverting the sign of magnitude. So it will be minus I naught. It was I naught here, well minus I naught here. Alpha to pi, pi plus alpha to 2 pi. So now you would expect some reduction in source current value, either average, RMS, or anything. So let's conduct RMS value of source current. You can go any standard way also, or just by looking at this waveform, since it is periodic with pi, okay. And if we are considering RMS, then direction doesn't matter here because anyway you are going to square the value. It means you are going to square the waveform, and in a square, this negative portion will go upward and it will look similar for each pi period. So it will be periodic with pi. So we can write it I naught the square of under root. It is just same way, just I am utilizing shortcut here. I naught square into the conduction period is pi minus alpha divided by total time period, whatever I am considering. If you solve it, you will get I naught under root pi minus alpha by. Did you get this, or should I derive in a standard format? Or do you know this, or should I explain it once more? Anything you want.
No, sir, got it.
Okay, perfect. So we computed ISRMS. Now, to compute distortion factor or total harmonic distortion in percentage, you need to know the Fourier series of this waveform. Okay, this waveform. So if you derive Fourier series, it will have some fundamental of 50 hertz along with some other harmonics. The same way which I told you in the beginning of the rectifier portion, that it will contain multiple harmonics, and I derived using switching functions also. Here I will also uh, draw so that you can easily visualize the thing. So it will start from, this is alpha by 2. Okay, this is pi plus alpha by 2. This is already pi plus alpha, so this will follow that kind of thing. If you compute Fourier series, or if you do the standard operation like Dirichlet condition A n, B n, and A naught, that kind of thing, you will. Sorry, I think I lost the connection. Am I audible now?
Yes, sir.
Okay, thanks. So this is the waveform uh, which you will obtain, this kind of waveform. So it will be shifted with alpha by 2. Due to this, you know, freewheeling operation, your waveform is kind of bit shifted, which will have some impact on values or parameters of the circuit. Can you guess which kind of parameters will be affected, which we are going to see? So first thing is that it has displaced by alpha by 2, and our supply voltage, if you see here, which is getting started from 0, and the fundamental, since supply is sinusoidal, so it will only have the fundamental 50 hertz, but for this square kind of waveform, it has already fundamental, it will have some third harmonics kind of thing, some fifth harmonic kind of things also. Sorry. So that kind of things will be present in this kind of waveforms. So those many harmonics and those magnitudes will depend on some parameters which we are going to see. Okay, so that's the thing here. So fundamental is shifted. Fundamental current, source current, is shifted from fundamental voltage. It means it will have some power factor angle, and this is known as fundamental displacement factor. Right? Fundamental displacement factor means only fundamental component of your source current is displaced from the fundamental voltage. So that is cos alpha by 2, right? Which used to happen cos alpha in other full bridge rectifiers. Why? Because after alpha it was continuous. So since it is continuous, so if you draw the Fourier series, you will get full wave from alpha to pi and so on. But here it is cos alpha by 2 only. Now we need to find G, which is distortion factor, that is IS1 RMS by IS RMS. Okay. And if you integrate this, or if you compute Fourier series of IS, you will get only odd number of things since it is symmetric. So if you shift it, you will see that it has even symmetric. It is, sorry, not even symmetric. It will be odd symmetric. If you shift it by alpha towards left, you will see what xt is equal to minus x of minus t. So this is the property of odd function. And earlier, if it was a full wave, means without any discon discontinuous conduction, it would have been 4 I naught by n pi sine in omega t. But now it lost some portion in freewheeling operation, so we have to compensate. And that factor will be compensated with cos n alpha by 2, right? So here, if you take n is equal to 1, you will see its magnitude has been reduced with the factor of cos alpha by 2. Okay, and that's the same thing will be reflected in your uh, magnitude. So if you take n is equal to 1, you will get is1 is equal to 4 I naught by pi. Earlier it was 4 I naught by pi for a conventional full bridge rectifier, but now it will be multiplied with cos alpha by 2. The higher angle of alpha, the higher delay you will provide to your thyristor, it will again face the same issue whatever it has been faced by single phase full bridge converter. The higher cos alpha or the higher firing angle, it will be higher, and your entire cos alpha by 2 will reduce, right? So this entire term will reduce, and you will lose in terms of magnitude of is1. And if you lost some portion in is1, that is the major portion which contributes to your active power, right? Your active power input, which will come from input vs is1 and whatever the fundamental displacement factor. So if your is1 is 0, you are not utilizing your input. You are not giving proper or whatever is required or whatever you could have provided earlier. And again, your alpha is going to increase, then input power factor will be compromised and your inverter rating will be increased. Okay, so that's the drawback here. Uh, However, you have gained in terms of number of switches. You reduced two switches, two diodes, but you have to compensate in terms of your power and power factor and all. So let me complete it with distortion factor, which is is1 RMS by is RMS, and which is 4 I naught by pi cos alpha by 2. And for RMS, we have to divide it by root 2. And is RMS was I naught under root pi minus alpha by pi. Okay. So now it is up to you to compute 2 root 2 by pi cos alpha by 2 divided by under root pi minus alpha by pi. So this is your distortion factor, which is a bit lengthy, but not much. If you know this expression, how to find it, it is the conventional expression just with multiplication of one factor due to reduction in due to that freewheeling operation. And if you know this, you have computed ISRMS, you are good to go with distortion factor. And once you computed this distortion factor, you can easily compute THD, which is nothing but 1 by G square minus 1, and you will get some value, which should be less than 48%, which we were getting in uncontrolled rectifier. So I think time is up. Any doubt in this one or anything?
No, sir.
Okay, then in next session we will see and we will solve some problems based on this semi-converter, and I hope probably from next week we will also start three-phase rectifiers. So, and I hope your preparation must be going well. You can start attempting your mock test on NPTEL website. You can visit that website. You can just log in and you can start attempting those mock tests. Are you guys attempting mock test? Because this is the high
Uh,
time. Yeah,
yes, sir.
great, great to hear. Okay, then
Thank you, sir.
we will meet again next week.